for central polynomials. If you consider 2 by 2 matrices, we have the Hamilton theorem, which gives that each matrix R squared minus the trace of the matrix times R plus the determinant of R times the identity matrix equals 0. This is the Hamilton theorem for 2 by 2 matrices. And if the trace of R equals 0, then we have that R squared is equal to minus the determinant of R times the identity matrix. So this matrix is scalar. And scalar matrices, they are in the center. So you have that R squared S equal to 0 for all 2 by 2 matrices S. And it's very easy to produce a matrix which is a trace 0. You simply take the trace, you take the R to be the commutator, so you have R1, R2 minus R2, R1, and of course this trace is 0. So this is exactly the commutator. So we have that the trace, the square of R1, R2, the commutator is a scalar matrix. And this simply implies that the commutator of R1, R2 squared S equals 0, which means that the commutator of x, y squared times z equals 0 is a polynomial identity for 2 by 2 matrices over a field. This identity is called the identity of Hall, and appeared already in the paper by Wagner 7 years before the paper of Hall, so it appeared also by Wagner in 1936 or 37. I think 36, but in the paper by Hall it appeared in another context that if a division algebra satisfies this identity, then it's either commutative or four-dimensional over its center. And Wagner, he had also not only that this identity for the matrix algebras, but also some other identities using this idea that the Hamilton theorem 1 R and R squared are linearly dependent. Okay, in his statement it was a little bit in another way, but he already had some identity which is an analog of this for any size of matrices. But here the important thing is that the commutator of xy squared is a central element evaluated when evaluated on the matrix algebra. And maybe if you try to do something similar for matrices of higher rank, of higher size, you see that you have problems. This idea doesn't work because it's difficult to make all the coefficients here 0. And in 1956, Kaplansky he gave a talk in the meeting of the American Mathematical Society where he presented 12 problems in ring theory which turned to be important for the next couple of decades. And his problem was, one of the problems was prove that such polynomials, such central polynomials exist for m and k when n is bigger than 2. Of course, it's easy to construct such polynomials cheating a little bit. For example, if you take for example 1 plus s twice n x1 x twice n is a central polynomial for n by n matrices. But this is not the question which you asked Kaplansky. This is really cheating. So if you make the problem more precise, here we should add that maybe the polynomial, so we want the polynomial is maybe multi-homogeneous, so homogeneous in each variable, and of course not a polynomial identity. Or even you can ask this polynomial to be multilinear. So this is not a good example. It was to avoid these examples. And now, in 1972, Formanek and a year later Razmisov constructed central polynomials for any size of matrices. And it was really something important that already in the next year, 1974, Jacobson, he wrote a book which was PI-Algebras, an introduction, written for the lecture, for the Springer lecture notes in mathematics, where the structure theory, the structure PI theory, was revised using central polynomials. So this is really important to know that central polynomials exist. And the two constructions, they are from quite different point of view. In our book with Formanek, when we decided to split the theory in two parts, he offered me, you give the construction of Razmisov and I give the construction of Formanek. Now I give the construction of Formanek. So in what follows, I give the construction of Formanek. And I give this for n equals 3 only, because it already contains the general idea. If you can do this for 3, you can do this in the general case. And the proof of Formanek, it was in the general case, of course. So maybe I start from here. So we do the following. We have some polynomial, maybe f, in commuting variables, 4 variables. So this is some right here, I, x1 in degree I1, x2 in degree I2, x3 in degree I3, x4 in degree I4. This is a polynomial in commuting variables. And I put the correspondence to this polynomial, something which maybe I write phi of f, depending on x, y1, y2, and y3. This is the following. I put all the x's to be equal, but in order to distinguish them, between them I put y's. So this is I here have x in power I1, y1, x in power I2, y2, x in power I3. This is a polynomial from the free associative algebra in 4 variables: x, y1, y2, y3. And now you see, we want to evaluate this on matrices. So we want to evaluate, so we have x, y1, y2, y3 are 3 by 3 matrices. Then it's easy to see that phi of f x, y1, y2, y3 is a linear combination of polynomials when x is any, and here you have matrix units E1, J1, EI2, J2, EI3, J3, and X is any 3 by 3 matrix. Because this expression is linear in the y's, so if you write down, you get linear combination. This it's sufficient to evaluate on these elements. Also, the matrix X is similar to a matrix of this form. I write here xi1, xi2, xi3. You have 0, and here you have any things. So, of course, when the field is algebraically closed, but from some point of view, it's enough to consider the matrices when you have here zeros. Because if you work from the, using Drensky topology, we may assume that X is similar to the diagonal matrix. If you don't like to use the Drensky topology, which is maybe something which is not known by all master students, for example, you can think that, so instead working over C, for example, we can find a sequence, okay, x1, x2, etc., going to the matrix X, such that each xi is similar to such a matrix xi, okay, 1i, xi2i, xi3i. And since this function is a continuous function, we can replace here X with a diagonal matrix. So this simply means it is sufficient to evaluate phi of X for such a matrix xi1 e11 plus xi2 e22 plus xi3 e33 xi1 j1 xi2 j2 xi3 g3. Okay, this is not enough that it's sufficient to evaluate for these purposes. For what purposes? But for our purposes it will be sufficient.